Okay, so I'm doing this in sort of like a YouTube tutorial style. Yes. So let's say we had a list of functional dependencies, and they start like this. Let's do C implies T. 2 is going to be HR implies C. 3 is going to be HT implies R. 4 is going to be HS implies R. And 5 is going to be CS implies G. So our relation here is going to be, get the right order. He wrote it as C, T, H, R, S, G. So this is our relationship here. So if we wanted to take the normal form or the BCNF of this, we have to start by splitting it on some certain functional dependency. So it's worth noting for a later part of the problem, the minimal key here is HS. I'm assuming since no one asked me that, they know how to compute that. But pretty much it's not present here at all on the right side, so we could try both of those. Obviously, it's also a functional dependency. So if we just tried all of them, you would be able to get the whole thing from just doing this one, doing the closure of this. Not important until later. You don't need to check that, I guess, for BCNF. But that would be like the beginning part of the problem. So to do BCNF here, what we want to do is we want to split on the functional dependencies. So when I say that, I mean we like make a tree. So let's split on functional dependency 1. It's usually where I always start. I think that's where most people start. So let's bring a functional dependency 1 over here. That's going to create a relation of C, T. And the reason that is because that's just, there's a C and a T in 1, so you bring them over here. Then you're going to head over here. The relation 2 is everything that's not in your right side, as well as the left-hand side of the functional dependency in the first one. So in this case, C also goes here. And that's what Dober calls the bridge. So what we're left with here is C, H, R, S, G. So obviously here C and T is contained in this set, so we have preserved functional dependency 1. We're done here. There's nothing else we can do here. Whereas in this side we have an H, R, and C, so functional dependency 2 is present. We have an HS and an R, so functional dependency 4 is present. We have a CS and a G, so functional dependency 5 is present. But unfortunately, we don't have a, what's it called? We don't have HR, wait. Did I write this wrong again? That'd be hilarious. HRC. No, okay. And we also have HR and C. I'm dumb. Which one did we lose? I can't read my own notes. Oh, sorry. We don't have an H, a T, and an R. So we've lost rule 3. I don't know why that took me so long. That's just because the T is not present here. That's fine, though. You can lose dependencies, I believe. Although, I think he might want the one on the exam to work out cleaner. So now from here, we need to split again. We want to get this down to a point where we can't split it anymore, pretty much. So I'm going to split on functional dependency 2. And that's going to give me relationship 2, 1. And that's going to be H, R, and C. So since the left-hand side of this is going to be H and R, that still gets carried over here. So we have H, R, and then SG. So now we need to split this, or let me write out the rules. So obviously rule 2 is contained here, and we're done there. We have rule 4 still present here because we have an H, S, and an R. But rule 5, since we don't have a C anymore, this does not stay. So that narrows down our choices here. We obviously have to split on 4 one more time. And that's going to give us our 2, 2, 1. And our 2, 2, 1 is going to be H, S, and R. And then R 2, 2, 2, which is going to be H, S, and G. So now you're done. We have preserved 4 here, and we're done. We ran out of functional dependencies in general. So now the answer to what the BCNF of these functional dependencies is going to be all of the leaves of this tree. And a leaf is just something that does not, or a leaf is just something that does not have a child. So it's going to be these 4. So that's the BCNF of these functional dependencies. Okay, so now for the third neural form, there is an algorithm you have to follow, and that algorithm involves a few steps. So let me do third normal form. So step I is going to be computing the minimal basis. So this is also like one of the earlier steps of the assignment, but it is the first step of the synthesis algorithm. So to compute the minimal basis, we need to check all of the functional dependencies here and see if we can go from the left-hand side to everything else in the entire relation. Again, the relation is everything that's present. So C, T, H, R, S, G. So you want to get to here from the left-hand side of these rules, but the trick for computing a minimal basis is we ignore the rule in question. So if we're gonna we ignore the what it implies. So for the first one, we're gonna try to see if we can go from C alone, the left-hand side of the first dependency, to the entire set, ignoring the rule C implies T. So without the rule C implies T, C goes actually nowhere. So we're just gonna have this. And that's fine. That means that we're good. If you can get every single thing in the set, that means that the rule in question is redundant. In this case, there are no redundant rules, so I will run through this really quick. So H and R, you can't go anywhere with that. Or 3, H and T, and H and T cannot go anywhere, I don't believe. Not on its own. 4, H and S. H and S cannot go anywhere on its own. And rule 5, C and S, which can get us C, S, T using rule 1. And that's it. We can never, and the way that this would break, oh, I'm sorry. I think I might have said get everything. What I mean to say is if we went from CS to something, like let's say we came somewhere and we were able to get C, S, T, G, for example, which is not possible, but because the rule here is CS implies G, if we could ever get a G, that means that the rule is redundant. So I misspoke there. But so that what I just did right there proves that we have a minimal basis because none of the rules are redundant. And the only difference between that and like the way you would turn something into a minimal basis is you just remove the redundant rule. So now we have step 2. Step 2 of the synthesis algorithm is creating fragments from your minimal basis. So since we're already a minimal basis, we're fine. And what I mean by fragments is we just make like a relation out of them. So let's do R1. This is for the first functional dependency, C, comma, T. And that's all you do. You just make a bunch of relations. So relation 2 is going to be this. Shit. Okay. It's going to be H, T, R. Rule 4 is going to be H, S, R. And rule 5 is going to be C, S, G. So there's a little bit of a shortcut here, but in general, all you do in this step now after we make the fragments and then we check for keys. So the trick here is, since we already computed at the beginning of this problem, I didn't show it, but we computed that HS is the key. So anything here that's going to contain HS is obviously going to be a super key, not a minimal one, but a super key that can solve it. And that is exactly the case here. If you did all of these out, you can't get all of it, I don't believe, except for rule 4, which contains H and S. So if we took H, S, R, and we computed the closure of it, so we can go from HS and R. We can go from HR using rule 2 to HSRC. We can go using rule 1. We can get HSRCT. And then using CNS, which is rule 5, we can get the whole set, which is H, S, R, C, T, G. So you could have done that in any order of rules. And obviously the point here is this is not a minimal super key. This is just a super key. That's all that matters. So now that we know that that's a super key, this is the relationship we want to target here. And then the point of step 3, the entire point, I can maybe compartmentalize it over here. I still want to have the fragments written out because it's related. So step 3, and the one I did in the doc is a good example of when it doesn't work, but this is a case where it does work. So because we had a key present here, we don't need to actually add anything. But if there was no key out of any of these fragments, right? If there was no super key, we would need to add a new relationship that we could define that is just a super key that works. I think it can be literally anything. And I think if he ever gave us one, there would probably only be about one option. He said that the functional dependencies are going to be pretty simple. But in this case, since relationship 4, which is H, S, and R, contains H and S, which is a minimal super key. We're done. So if there was no super key in these sets, we would need to make a new one, and that's the example I have in the Google Doc. But that is how you do BCNF and third normal form with an example I'm sorry it was kind of long, but hopefully it helps.